In the previous lecture, we were examining the dynamics of a two-mass system, two masses connected together by a spring, with an input force Fi acting on mass 2. And we found the transfer function between Fi and the displacement of mass 2, x2. This transfer function had a fourth-order denominator, and we labeled it g2. The numerator was second order, so this transfer function has 2 zeros and 4 poles. We found these zeros and poles, and we plotted them in the complex plane. The transfer function had 2 poles at the origin, which we referred to as rigid body poles. It also had 2 poles on the imaginary axis at plus and minus j omega n. These were the flexible mode poles. Finally, this transfer function had 2 zeros, also on the imaginary axis, at plus and minus j omega naught. We'll now examine the transfer function between the input force Fi and the displacement of mass 1, x1. Recall now that we found the transfer function between the input force Fi and the displacement of mass x2. And this transfer function was given by m1 s squared plus k divided by m1 m2 s to the fourth plus k times quantity m1 plus m2 times s squared. We also found the equation relating the displacement of mass 2 to the displacement of mass 1, and that was x1 of s equals k divided by m1 s squared plus k times x2 of s. So now I can substitute the first equation in this page into the second equation to eliminate x2 of s. So this will give me the relationship between the input force Fi and the displacement of mass 1, that is x1. So this is a different transfer function. Previously we found the one between Fi and displacement of mass 2, and now we can find it between Fi and displacement of mass 1. I'll label this transfer function g1 since it's the transfer function between the input Fi and the output displacement of mass 1. And this transfer function is k over a denominator consisting of 2 terms. One is s squared, and the other is the quadratic factor m1 times m2 times s squared plus k times the quantity m1 plus m2. So we found the transfer function between Fi and x1, and also the transfer function between Fi and x2. The first of these is labeled g1, the second one is labeled g2, and both are shown here. And what I want you to notice is that both these transfer functions have the same denominator. They have different numerators, however. And that's key. So transfer function g1 and g2 will have the same poles since they have the same denominator. But transfer function g1 and g2 will have different zeros. g1 doesn't have any zeros, and g2 has a pair of zeros that are imaginary. This is a key aspect of these mechanical systems. They will have the same poles independent of what output we use, but they can have different zeros depending upon what output we use. Let's recall what the poles are. When we found the transfer function between Fi and the output x2, we found the poles to be 0, 0, minus j over square root of k over me, and plus j over square root of k over me, where me was m1 times m2 divided by m1 plus m2. So these were the poles for the transfer function between Fi and displacement of mass 2. They'll also be the poles between Fi and the displacement of mass 1. For g1, this transfer function has no zeros, but for G2, the zeros are plus and minus j square root of k over m1. Here are the poles in the complex plane when x1 is the output. We have 2 poles at the origin and 2 on the imaginary axis. The poles at the origin correspond to the rigid body modes of the system, and the poles on the imaginary axis correspond to the flexible modes. There are no zeros in the transfer function between input fi and output x1. When x2 is the output, the poles and zeros are distributed as shown here. We have the same poles, 2 at the origin and 2 on the imaginary axis. But we also have 2 zeros located on the imaginary axis. To finish this example, we'll compare these 2 figures. They show the poles and zeros, where the input is fi and the output is x1 in the top figure and x2 in the bottom figure. We've now finished our examination of the first of 2 cases. In our next lecture, we'll examine another 2-mass system. The following is some supplementary material that I thought you might be interested in. It's a feedback way of looking at our 2-mass system. When we were developing these equations, we had an intermediate step, which I'll now draw your attention to. We found that x1 of s was equal to k over m1 s squared plus k times x2 of s. And then we found x2 of s was related to x1 of s and fi of s through the second equation on this page. We'll now make a block diagram of the first equation and the third equation. The first equation has x1 of s equal to the transfer function k over m1 s squared plus k times x2 of s. That's represented by the line at the bottom of the block diagram, where x2 of s goes into the block k over m1 s squared plus k, and out comes x1 of s. The third equation, x2 of s equals 1 over m2 s squared plus k times the quantity k times x1 of s plus fi of s, is represented by the upper block and the summation junction. You can see at the summation junction I have fi plus k times x1 of s. That's labeled sum of the forces, sigma f. And that goes into the block 1 over m2 s squared plus k to produce x2 of s. So you can see the third equation is the summation junction and the transfer function 1 over m2 s squared plus k. The signal labeled sigma f is the sum of the forces acting on mass m2. This block diagram shows the interaction between the motion of the 2 masses, x1 and x2. It shows their interconnected dynamics. We have x2 responding to the external force Fi and k, the spring constant, times x1. And then we have x1 responding to x2 through the transfer function k over m1 s squared plus k. The block diagram shows that the motions of mass 1 and mass 2 are coupled together, with the motion of x1 affecting x2 and then the motion of x2 affecting x1. I hope you found this feedback way of looking at the relationship between the motions of mass 1 and mass 2, interesting.